So the topic is Doppler's effect. It can be applied to both electromagnetic wave and mechanical wave, mean it can be applied to all types of the waves. Suppose we apply to the sound wave. This is the source of the sound and emitting constant intensity sound in all possible directions. The source is stationary. It is emitting sound in all possible directions. The speed of the sound in all direction is v, which is usually 330 meter per second in air. Its frequency is f and wavelength lambda in all direction. So these are the three properties, v, f, and lambda. And two observers are standing in two different directions. This is the observer A and this is the observer B. Both are hearing sound of speed v, frequency f, and lambda v. Now, observers are stationary, source is stationary, so the wave fronts of the sound wave approaching to both observer are like this. And the gap between two wavefront is representing lambda. So same at A observer, same wavelength lambda. Source stationary, observers are stationary, so the wavelength same for both observer, right? Now, this source starts traveling to one of the observers. Suppose it travels in this direction with speed Vs. V is the speed of the sound in the air, mean the still air, and Vs is the speed of the source towards A. So this Vs is the speed of the source. When the source of the sound moves towards A, the wave travels again, both direction, but now the air is opposing the sound. So air is traveling now in this direction because air is resistive force is opposes the motion. When the source is traveling towards the observer A, then the wind is blowing, this air is flowing towards the observer B, so opposing the motion of the source. Now, according to theory, if the source moves with the Vs, then the wind is also moving with the same speed Vs. So the speed of the source is also equal to the speed of the wind. So Vs is the speed of the wind because the source is moving with this speed. Now, due to opposite direction wind, the resultant speed becomes v minus vs towards the observer. Resultant speed decreases because the wind is opposing the motion of the source, but the sound going to be observed towards this B observer will be v plus vs. So speed of the sound towards A will decrease because the wind is blowing in the opposite direction. But for the observer B, the sound is going and the wind is blowing in the same direction, so both speed increases, mean the resultant speed increases. So here the resultant speed decreases and here the resultant speed increases. So when source travel towards the observer, resultant speed decreases. When the source moves away from the observer, then the speed resultant increases. Okay, now due to decreased speed, the distance covered by the wave will decrease, hence there will be decrease in the wave fronts. Now the wave fronts are closer to each other because the wave front represents the wavelength, distance covered by the wave, speed decreases, so wave front gap decreases. And towards the observer A, the speed of the sound increases, so the wave front increases, mean the gap increases. Now, the wavelength observed by the observer A, lambda naught, and here also lambda naught. So this lambda naught is decreased wavelength, and this is increased wavelength. Now, according to the formula, V is equal to F lambda. So this decreased wavelength lambda will be equal to, lambda is equal to V divided by F. So the resultant V is V minus Vs over F. And here, this increased lambda will be due to increased speed, V plus Vs divided by F. So look, when the source travels towards the observer, speed decreases, wavelength decreases. When the source moves away from the observer, speed resultant increases, and this lambda naught also increases. Now, according to theory, frequency and wavelength both are inversely proportional. So when wavelength is decreasing towards the observer, lambda naught is the decreased. Definitely the observed frequency will be different. It will increase. And here, when the lambda naught increase, the observed frequency will be decreased. When the source is moving towards the observer, speed decreases, wavelength decreases, but the frequency increases because the frequency inversely proportional to lambda. When the source moves away from the observer, speed resultant increases, wavelength increases, but the frequency decreases. Now, what is the observed frequency? V is equal to F lambda. So F naught is equal to V divided by lambda naught. So the frequency observed will be F naught equal to V divided by lambda naught. Now substitute the value of lambda naught. V divided by lambda naught is V minus Vs over F, mean it becomes F is equal to Vf divided by V minus Vs. This is the observed frequency when the source travels towards the observer. What is the resultant speed? V minus Vs. What is the wavelength observed? This is the formula. So what is the frequency observed? This is the formula. Now, come to this, when the source moves away from the observer, the resultant speed increases, wavelength increases, but the frequency decreases. So this decreased frequency will be V divided by lambda naught, mean V divided by lambda naught is V minus V plus Vs divided by F. So the observed frequency will be Vf divided by V plus Vs. This is the formula when the source is moving away from the observer, and this is the formula when the source is moving towards the observer. So what is F and what is V? F is the actual frequency of the sound. V is the actual speed of the sound in air, which is 330. And what is Vs? This is the speed of the wind or speed of the source. And F naught is actually the observed frequency. So when the source is coming towards the observer, its frequency increases, the sound becomes more sharp. But when the source is moving away from the observer, its frequency decreases, so the sharpness of the sound decreases. Hence, when the source of the sound, when the source of the wave moves relative to fixed observer, there will be apparent change in the frequency and wavelength. This effect is called Doppler's effect. When source of wave moves relative to fixed observer, there will be apparent change in the frequency, wavelength of wave. This is called Doppler's effect. If this is applied to light, to stars, if the wavelength observed increases, then this is called redshift. If the wavelength lambda naught, mean observed wavelength, decreases, then this is called blue shift. These are the terms used. Redshift, blue shift.